Okay, thanks a lot for the introduction. I guess in the presentation, in Attila's presentation, he shows a very good background about the real-time PPP services. So in my talk, I will show you in the case we have the real-time global ionospheric maps, how could we compute the associated accuracy in information, or the so-called RNS map. As you may well know, within the IGS, we have the real-time IGS-SSR standards, especially for the real-time PPP applications. And such real-time SSR standards have been published 4 years ago, and its current stage can only support the services for the multi-GNSS, I mean, supporting the whole 4 GNSS constellations for the real-time satellite orbit, satellite clock, code and phase biases, as well as the real-time global ionospheric maps. So in 2 years ago, I mean 2022, we have a roadmap for the continuity of the IGS real-time activity. For its phase 1, the IGS real-time working group would like to extend the IGS-SSR format with some new messages, especially for those information about the altitude, satellite, APC, QAM offset, as well as the PCV and the GDV correction information. For its phase 2, we would like to define a greater format, especially on how could we provide the ionospheric accuracy information associated to its real-time VTEC products for its phase 2, especially for the follow-on PPP ambiguity solutions. I mean, to shorten the convergency of the PPP application, we would like to define satellite-based slanted information to further shorten the convergency time of the real-time PPP. And outside, we had done some analysis work, especially at first for the phase 3 of the real-time analysis activity. We have now, for the real-time modeling on those different scales, and first on the global scale, very similar to the RTCM or the IGS real-time standards. We now make the real-time global VTEC modeling based on the single layer assumption using the spherical harmonic functions. And in addition to the global VTEC modeling, and outside we also have our regional slanted or VTEC models, as well as the local satellite-dependent aesthetic ionospheric model. I guess some of the, especially for the PPP RTK applications, we are now focused on the local satellite-dependent aesthetic modeling. So here I give some examples of our real-time ionospheric product. The first one is our combined real-time global ionospheric maps. The performance, I would say, are quite similar to the IGS can provide combined GIM product, and we can provide such combined real-time GIM product to the IGS since 2 years ago. And for the local slanted ionospheric modeling, and also this area, I would say, is located in the north part of China, and outside we can now reach about modeling accuracy about 0.5 type unit for each satellite. Then when it comes to the accuracy information of this provided ionospheric product, about 2 years ago, especially within the IGS real-time community, we had one questionnaire. So from those questionnaires, we also got the information that in addition to the provided VTEC or aesthetic ionospheric corrections, the associated accuracy information are also highly required. So if we would like to see how those accuracy information can be calculated, we first have a look at the RMS map provided by the IGS, especially from those rapid and final GIM product. And we can see that in our analysis, we can see that at first the algorithm for those RMS computation have not yet been published by any ionospheric analysis centers by now. And we can see in the figures those accuracy information by different ionospheric analysis centers differs from each other. So in our real-time, in our calculation of real-time ionospheric accuracy information and outside, and first we follow our RMS calculation algorithm, which can be applied for our rapid GIM computation. And you can see for the accuracy information, we included two parameters here. One is the scale, which will magnify the model provide the precision information, which would be calculated from our from the variance and covariance measures from our spherical harmonic fitting. Here gives some one examples for one epoch how those real-time accuracy information can be provided to the users, and also in our use of our own real-time RMS map, especially in the single frequency PPP, we have found some problems in those provided RMS map. Then we have made some updates on the algorithms, because in the real-time tech map computation, we can imagine the uneven distribution of those real-time GNSS stations. So for the real-time accuracy information computation, we took those updated algorithms, which can, I would say, will balance the different accuracy for those VTEC calculated with a dense network of GNSS stations, and those VTEC calculated with how to say, the tech information which might be provided with no contributing real-time GNSS stations. Here I give an example. Here is one example is the FK information, because I did not give so much details here. The FK parameter here we adapted here is to adjust the residual ionospheric information, because as we all know, the residual ionospheric does not form the normal distribution, so we introduced the FK here. In addition, also in our algorithms, we also considered the different distributions as well as the contributing real-time IPP, the real-time number of the contributing ionospheric information here. In these slides, I give an example of our real-time GNSS stations we used for the RT-GIM computation on the top panel is associated RT-VTEC corrections, as well as those real-time RMS information computed by our newly proposed algorithm. And for the validation, we have made a comparison of those RMS maps computed by two different methods using about 20 global IGS stations, and the test covering about the 3 months of last year. In addition, the CAS and code provided the regular and final GIM product are also included for the following on analysis. And in our analysis, I would highlight here, we would like to make such validation from the perspective of the protection level of our provided RMS band. About 4 years ago, we have one paper which has been published in Journal of Geodesy to show how the validation can be done using the GNSS DSTEC analysis. I would not go so deep here. I would mention that for our analysis, we have at first the ionospheric Stanford light plot analysis. In addition, we also have made the correlation analysis as well as the RMSE analysis. Here is we have made a comparison of the RMS maps provided by the old and new algorithms. Although the RMS information computed by those two methods can well capture those ionospheric residuals, we can from here those RMS information computed by our newly proposed method. I mean the volume we can see from in the y-axis are quite smaller. For the correlation analysis, we can see from the figures that those correlation coefficients computed by the new method are slightly larger than the old method. Here is the table made a comparable comparison not only for the real-time RMS information, but also we made a comparison with the rapid and final GIM product provided by code and our own. We can see that especially for the correlation analysis, our newly algorithm now have shows the highest correlation coefficients, even compared to some RMS information provided by the rapid and final GIM product. Then for the RMSE analysis, the smaller volume means the better performance of the provided RMS information. And we also have such a table make a summary. And also we have applied our provided RMS information to the B23 only 1 Hz PPP, which shows, I would say, a better performance compared to, in the case we did not consider the ionospheric information in the PPP application. Here is some conclusions now, and this is all I would like to present. Yeah. Thanks a lot.